Yes. Yes. Good morning. In the last class, we discussed about the concept of the Henry's law, mathematical form of the Henry's law, and problems based upon it. Now, what are the applications and limitations of the Henry's law? Whereas, according to Henry's law, it depends upon pressure and temperature. Increase in pressure increases the solubility of the gas in liquids. Decrease in temperature also increases the solubility of the gas in the liquids. But at too high pressure and too low temperature, Henry's law not holds good. Under moderate pressure and moderate temperature, only the Henry's law is applicable. Therefore, first limitation of the Henry's law is not applicable under too high pressure and too low temperature. Some of the gases which undergoes interactions with the liquid or chemical reactions with the liquid, those gases are not suited to dissolve according to the Henry's law, and the gases which undergoes some dissociation in the liquid, that does not involve in this category. Therefore, four important limitations of the Henry's law: under high pressure, under low temperature, and the gases which undergoes dissociation in the liquid and which have capacity to interact with other liquids, these are not used in Henry's law. Now, what are the advantages of the Henry's law? In the last class, we discussed about how these soft drinks are manufactured. Usually they are passing carbon dioxide under high pressure. Therefore, in the preparation of these soft drinks and beer, they are passing carbon dioxide under high pressure. This is one of the important application of the Henry's law. You know, but the higher altitude from the sea level and under that is the surface of the water, whereas pressure of the system, suppose under lower portion of the sea at a higher altitude from the sea level, whereas the pressure that decreases, pressure is very less, here pressure is very high, pressure is very high. This is inner sea, here mountains. Whereas the mountain climbers, whereas if suppose they are higher altitude from the sea level and under the bottom portion of the sea, the pressure is more. Therefore, scuba divers who are working below the seawater, here the pressure is maximum. Therefore, according to the Henry's law, that solubility of the gas in the liquid or in the fluid is more. Blood is a fluid, blood is a liquid. Therefore, more quantity of the nitrogen that may be dissolved in blood under high pressure, that is bottom portion of the sea. And one more thing, whereas the mountain climbers, whereas they are operating under low pressure, therefore the dissolution of the oxygen in the blood is very less at higher altitude from the sea level. Therefore, the mountain climbers, where at a higher altitude from the sea level, they have lesser concentration of the oxygen in the blood. Whenever the oxygen concentration in the blood is very less, it affects the central nervous system. Therefore, the thinking capacity or activation of the brain, that is very less at higher altitude from the sea level. This phenomenon is called anoxia. Whereas the bottom portion of the sea, the pressure is very high, therefore higher concentration of the nitrogen that is dissolved, and when these vapors that come to the surface, therefore the pressure is decreased Therefore, the nitrogen concentration that is decreased and it affects that of the veins. Therefore, that leakage of the blood will occur. This phenomenon is called as a bend. Therefore, bend means lower portion of the sea, and anoxia means at higher altitude from the sea level. These two are important medical terms that operates under Henry's law. Now, there are three important applications of the Henry's law. One is mountain climbers. They are facing the problem because of the lower concentration of the oxygen in the bloodstream and higher concentration of the nitrogen that can be observed in scuba divers. When they comes to the surface of the earth, then what happens? The pressure is decreased and nitrogen concentration that appears in the form of the bubbles, it blocks the capillaries and rushes the blood from the nose. Now the bend and anoxia, these two important, very important. Now this is about the application of the Henry's law and limitations of the Henry's law. Now very important. Now the next concept, that is the volatile liquids. Volatile liquids. Vapor pressure of the liquid solutions. Vapor pressure of liquid solutions. Vapor pressure of liquid solutions. Vapor pressure of liquid solutions. Now you know about the liquids. Liquids are categorized into two types. They are called as volatile liquids and non-volatile liquids. Non-volatile liquids. Prerequisite. What are volatile liquids? Liquids with low boiling point. Liquids with low boiling points and liquids with high boiling point. High boiling point. Low boiling point liquids are called volatile liquids. Low boiling point means which undergoes easy vaporization. For example, organic liquids like ethanol, acetone, your petrol and diesel. These type of the liquids, when they are exposed to atmospheric air at laboratory temperature, they undergoes vaporization. These type of the liquids are called volatile liquids. Whereas high boiling point liquids, for example, water, whereas benzene, whereas at high temperature and elevating the temperature, they undergoes vaporization. Therefore, the boiling point of such liquids are very high. In general, low boiling point liquids are called volatile liquids and high boiling point liquids are called non-volatile liquids. Now, what do you mean by vapor pressure? Vapor pressure and partial pressure. Partial vapor pressure. Partial vapor pressure. You know about the mole fraction in the last class? Mole fraction. That is the ratio of the suppose Na divided by Na plus Nb or Nb divided by Na plus Nb. Assume that was A is solute. A is solute and B is solvent. Mole fraction of solute, mole fraction of solute and mole fraction of solvent, mole fraction of solvent. mole fraction of solvent. Assume it is XA, and assume that is equal to XB, mole fraction of solute and mole fraction of solvent. Mole fraction of solute is nothing but the number of moles of the solute divided by number of moles of the solute plus number of moles of the solvent. It is the ratio of the number of moles of the individual component to the total component of the mixture, the number of moles of total component of the mixture. Now, mole fraction of the solvent, assume B is a solvent, NB divided by Na plus NB. Number of moles of the solvent divided by number of moles of the solute plus number of moles of the solvent. I will call it as XB. What about the mole fraction of the solvent? Mole fraction in general, it is the ratio of the number of moles of the individual component to the number of moles of the mixture, total mixture. Now, anyhow, in general, XA plus XB, that is always equal to 1. In the last class, we proved that is the sum of the mole fractions of individual component of the mixture is always equal to 1. If it is a binary system, when we have two components, preferably if it's solute and solvent, or two liquids, whatever it may be, therefore sum of the mole fractions of the total component of the mixture is always equal to 1. Now, what do you mean by the partial pressure? Partial pressure is equal to mole fraction into total pressure. Mole fraction into total pressure. Mole fraction into total pressure. That is equal to partial pressure. If suppose the mole fraction is suppose XA into total pressure, that is equal to P, or mole fraction of XA is given by Na divided by Na plus Nb. This is the mole fraction of this one component into total pressure of the system, suppose that is equal to P. This is called partial pressure of the component A. Partial pressure of the component A. Partial pressure of the component P is given by, that is the mole fraction of the component P, that is Nb divided by Na plus Nb into the total pressure of the system, that is equal to P. Therefore, that is called as a partial pressure of the B. Very important, this is the formula. Partial pressure of the system is given by the product of the mole fraction and total pressure of the system. That you already studied in our previous class, that is the mole fraction. This is very important in order to discuss the vapor pressure, and in future there is Rolle's law. These are the very important concepts. And very important, one more thing, that is azeotropic mixture. These are the very important concepts. Azeotropic mixture. Now, what do you mean by azeotropic mixture? Where is if two liquids A and B, they have the same boiling point, then that type of the mixtures are called azeotropic mixture. Liquid mixtures with constant boiling point, liquid mixtures with same boiling point are called azeotropic mixture. If suppose the liquid A is mixed with that of the liquid B, then both forms at certain point the constant boiling mixture, that at this stage the liquid A and liquid B, they have ability to form the azeotropic mixture. Constant boiling mixtures are called azeotropic mixtures. Now, these are very important terminologies that we require to discuss the further class. Now what do you mean by vapor pressure? Suppose this is one container, consists of the liquid, up to this extent. On heating the liquid, then it forms vapors. On heating the liquid, it forms the vapors above the surface of the given liquid. Above the surface of the given liquid. Because this molecular velocity will be more for these vapors. Molecular velocity will be less for the liquid, given liquid. Now this is liquid and this is vapor. This is heat energy. On heating the given liquid, the molecular velocity of the liquid will be increased and they forms the vapors above the surface of the given liquid. Now these are in vapor state. These are in vapor state. They undergo collision with one another and hence they have ability to create pressure. The pressure exerted by the vapor above the surface of the given liquid, that pressure is called as a vapor pressure. That pressure is called as a vapor pressure. What do you mean by vapor pressure? The pressure exerted by the vapor, the pressure exerted by the vapor above the liquid surface where both phases are in the equilibrium state now. Vapor is in equilibrium with the liquid. Vapor is in equilibrium with the liquid. Vapor is in equilibrium with the liquid. Now this is called as a vapor pressure of the liquid solutions. Vapor pressure of the liquid solution. Now very important, what do you mean by vapor pressure of the liquid solution? Pressure exerted by the vapors above the surface of the liquid where the vapor is in equilibrium with that of the given liquid is called vapor pressure at the given temperature. At the given temperature. Now it depends upon the various factors. Vapor pressure, it depends upon the temperature and it depends upon the nature of the liquid. It depends upon the nature of the liquid. Whereas suppose you have the different liquids. We have the different liquids. Liquid A, liquid A, liquid B and liquid C and liquid D. In your entrance exam they will give the problems that based upon this. Which one of the following that possess the highest vapor pressure are more volatile? Suppose this is 100 millimeter of mercury. Now this is about 200 millimeter of mercury. Now this is about 300 millimeter of mercury and this is about 400 millimeter of mercury. In your entrance exam they will give the problems like this. Suppose the four liquids A, B, C, D having the vapor pressure of 100 millimeter of mercury, 200 millimeter of mercury, 300 millimeter of mercury and 400 millimeter of mercury. Then we arrange the following in increasing order of the boiling point or volatile nature. Now, the liquids with higher vapor pressure, they are more volatile. Liquids with higher vapor pressure, they are more volatile. Therefore, D is more volatile. D is more volatile compared to that of the C, compared to that of the B, compared to that of the E. Therefore, D is more volatile. I will give a small hint how to predict the more volatile nature. Among the various liquids which possess the higher vapor pressure at given temperature, then that is more volatile liquid. Okay. Now consider very important, that is Rolle's law. In vapor pressure of the liquid solutions. Suppose the two liquids which are mixed, A and B. Therefore, vapor pressure of the liquid solutions. Now consider, now that is directly proportional to the mole fraction. Suppose this is a 1, liquid 1 is mixed with that of the liquid 2, liquid 1 and liquid 2. When both are mixed, liquid 1 plus liquid 2, liquid 1 when it is mixed with that of the liquid 2. Then for this liquid 1, the pressure, pure pressure, that is equal to P01. For liquid 2 alone, the pressure exerted in a pure state, that is equal to P02. And mole fraction of this liquid, that is equal to X1, and mole fraction of this liquid, that is equal to X2. Now this is vapor pressure in pure state. Vapor pressure in pure state without mixing. Pure state means without mixing. Without mixing. Here this corresponds to vapor pressure in pure state. In pure state, that is without mixing. Without mixing. This corresponds to the mole fraction of liquid 1. Mole fraction of liquid 1. This corresponds to the mole fraction of liquid 2. Mole fraction of liquid 2. Mole fraction of liquid 1 and mole fraction of liquid 2. Let us consider two liquids, 1 and 2. Let us consider two liquids, 1 and 2. I will designate as the liquid 1 and I will consider this liquid 2. When two liquids are mixed, we have liquid 1 and liquid 2. Now the pressure exerted by vapor pressure of the liquid 1, I will designate it as a P01, and vapor pressure of the liquid 2 I designated as a P02, and mole fraction of the liquid 1 is designated by means of X1, and mole fraction of the liquid 2 is designated by means of the X22. After mixing, then I will consider this is a P1 and this is equal to P2. Whereas a P1 and P2, that refers to the partial pressure, that is vapor pressure exerted by the liquid 1 and liquid 2. Therefore, according to the Rolle's law, that is P1 is directly proportional to the X1 and P2 is directly proportional to that is of the X2. That is the mathematical form of the Rolle's law. It is the modified form of the Henry's law also. Whereas according to the Rolle's law, the partial vapor pressure exerted whenever the two liquids are non-volatile liquids of mixing, that is a P1 is directly proportional to X1 and P2 is directly proportional to the X2. Now P1 is equal to, by removing the proportionality term, this is called P01 into X1. Remove this one, proportionality, P2 is equal to P02 into that of the X2. Whereas if it is X1, therefore P1 is equal to P01. Whatever by the mole fraction, this is the mole fraction of the liquid 1, this is the mole fraction of the liquid 2. Now, we will consider. Now suppose the two liquids are there. Now this P0 one, that is the mole fraction. Suppose the mole fraction of the solute, mole fraction of solvent is equal to, assume that is 0.95. Mole fraction of the solvent is equal to 0.95. What about the mole fraction of the solute? Because the sum of the mole fractions that is always equal to 1. Therefore, mole fraction of the solute is equal to 0.05. Now, under this condition, the lowering of the vapor, that is vapor pressure, that is equal to, that is 0. That is the mole fraction of the solute itself. If we consider the solute, this is also considered solute. If we consider the solvent, this is also considered solvent. That is the binary mixtures. That is not necessarily that is the two liquids, liquid mixtures, even in case of the solid liquid mixtures. This is about the mathematical form of the Rolle's law. Now suppose when two liquids upon mixing, what about the net pressure when two liquids upon mixing? The total pressure according to that of Dalton's law of the partial pressure, that is given by P1 and P2. Therefore, P1 plus P2 is given by, that is a P0 1 into x1 plus P0 2 into x2. This is according to that of the Dalton's law. Therefore, Rolle's law followed by means of the Dalton's law. What about the statement of the Dalton's law? According to the Dalton's law, the gases which does not react chemically with one another, the total pressure exerted by the gas, that is equal to sum of the partial pressures exerted by the gas molecules. This is mole fraction and this is total pressure, therefore that is equal to partial pressure. This is mole fraction and this is the total pressure, that is equal to partial pressure. Therefore, when two liquids are mixing, the vapor pressure exerted by means of the total liquids, that is equal to P1 plus P2 is equal to P0 1 into x1 plus P0 2 into x2. When you plot the graph, vapor pressure and mole fraction, that given by means of the straight line. Now try to solve the problem. Vapor pressure of the pure liquid A and B, vapor pressure of pure liquid A and B. Vapor pressure of pure liquids A and B. Pure liquids A and B, A and B are 450 and 700 millimeter of mercury, or 450 and 700 millimeter of mercury, respectively. At 350 Kelvin. At 350 Kelvin. Find out the composition of the liquid mixture. Find out the composition of the liquid mixture. Find out the composition of the liquid mixture. If the total vapor pressure, is 600 millimeter of mercury, also find the composition of the vapor phase. Also find the composition of the vapor pressure. Composition of the vapor phase. Composition of the vapor phase. Composition of the vapor phase. Now this problem that based upon the Rolle's law. Suppose data, this is liquid A, this is liquid B, liquid A and liquid B. Now vapor pressure of the pure liquid. Vapor pressure in pure form. I will call this as P naught A. P naught A is given by 450 millimeter of mercury. 450 millimeter of mercury. And liquid B, that is 700 millimeter of mercury. This is equal to P naught B. P naught B. Here mole fraction is not yet given. Assume the mole fraction of liquid A is equal to XA, mole fraction of liquid B that is equal to XB. You know that XA plus XB that is equal to 1. Therefore, what about XA? XB that is equal to, can we write this is 1 minus XA? XB is equal to 1 minus XA. When both upon mixing P1 plus P2 or PA plus PB after mixing, that is given as 600 millimeter of mercury. This is after mixing. after mixing. These are data. This is about the data. Now what about according to that of the Rolle's law? That is a P total that is given by means of P1 plus P2. That is considered as a P total. Therefore, P total is given by means of P naught A into XA plus P naught B into XB. But you know that the XB is equal to 1 minus XA. Therefore, that is given by means of P naught A into XA plus P naught B into 1 minus XA. 1 minus XA. This is in terms of P total. P total. Now P total is given. P total is given. That is a 600 millimeter of mercury. P naught A is given. That is 450 millimeter of mercury into XA plus PP is given. That is 700 millimeter of mercury. That is 1 minus XA. You have to evaluate XA first. Therefore, this is equal to 450 into XA plus 700 minus 700 into XA. That is equal to 600. 600. Now this is minus 700, this is plus 450, that is equal to 250. Therefore, total now it is equal to 600 minus 450 XA minus 700 plus 700 XA, that whole is equal to 0. That whole is equal to 0. Now it can be rewritten as minus 100 minus 250. Sorry, this is equal to 700. 600 minus 700, that is equal to minus 100. This 600 and minus, that is equal to, this is 450 and this is 700, that's minus 250. That is into XA. That is into XA. Or that is XA 100 is equal to 250 into XA. What about the value of the XA? XA is given by XA is equal to how much? That is 0.4. XA is equal to, on simplification, that XA becomes 0.4. Now if XA is equal to 0.4, what about the value of the XB? XB is equal to 1 minus 0.4, that is equal to 0.6. That is equal to 0.6. Therefore, the mole fraction of the A is 0.4 and the mole fraction of the B is equal to 0.6. Now, also find the composition of the vapor pressure. Now, the mole fraction is known for XA and vapor pressure of the pure component of the system PA naught A is given. Therefore, multiply these two, then it gives the composition of the vapor pressure of vapor pressure of the A. Similarly, when you multiply this XB 0.6 into 700, that gives the composition of the vapor pressure. Composition of the vapor pressure of liquid A. Composition of the vapor pressure of the liquid A. Composition of the vapor pressure of liquid A. That is given by PA is equal to P naught A into XA. P naught A is given, that is a 450, and XA is given, that calculated, that is 0.4. Multiplying these two, that gives the P naught A in terms of millimeter of mercury. What is the multiplication of these two? That seems to be 180 millimeter of mercury. 180 millimeter of mercury. And composition of vapor pressure of liquid B. Composition of vapor pressure of liquid B. Where is the PB is given by, it is PB is given by P naught B into XB. Now the XA is 0.4 and XB is equal to 0.6. P naught B is given, that is 700 millimeter of mercury, 700 millimeter of mercury, and XP is given, that is calculated already, that is 0.6. Therefore the total is equal to, I think that is a 420 millimeter of mercury. 420 millimeter of mercury. Now cross check it. PU, that is a PA plus PB, that is a partial pressure of the liquid A and partial pressure of the liquid B, that is 180 millimeter of mercury, 180 millimeter of mercury plus 420 millimeter of mercury. The total is equal to 600 millimeter of mercury. 600 millimeter of mercury. It is already given in the problem, 600 millimeter of mercury, and hence what's good, the problem is correct. Usually this type of the problems they are asking in part D, that is a 28th question A. It is purely based upon numericals. They are asking this type of the problems. Okay, you have to solve the problems like this. Usually in solution chapter, the problem numerical and definitions of the terms, they are very important. Yes, one more problem. Heptane and octane forms in ideal solutions. Forms in ideal solutions at 373 Kelvin. The vapor pressure of two liquid components the vapor pressure of the two liquid components are 105.2 kilopascal and 46.8 kilopascal respectively. What will be the vapor pressure of the mixture? What will be the vapor pressure of the mixture? vapor pressure of the mixture of 26 gram heptane, 26 gram heptane and 35 gram octane, 35 gram octane. First you have to calculate the mole fraction of the octane and mole fraction of the heptane. Then they mention the pressure of the system, that is 105.2 kilopascal and 46.8 kilopascal. Then afterwards, by using the Rolle's law application formula, you can calculate the total vapor pressure of the mixture. Now what is the formula of the octane and heptane? Heptane and octane. Heptane, it is an alkane series. Hepta means 7 number of the carbon atoms, that is equal to C7 alkane series. 7 into 2, 14 plus 6, that is equal to 16. That is a formula. Octane. Octa means 8, that is a carbon number 8. Then since it is alkane series, CnH2n plus 2, 8 plus 8 into 2, 16, 16 plus 2, that is equal to 8, 18. Therefore, the molecular formula of the octane is equal to C8H18. You know that the carbon atomic mass 12, hydrogen atomic mass 1. Therefore, calculate the molecular mass of the heptane. Molecular mass of heptane. Molecular mass of heptane. Heptane, that is equal to C7H16, that is given by the number of carbon atoms, that is a 7 into atomic mass of carbon, 7 into atomic mass of carbon plus 1 into atomic mass of hydrogen, 1 into atomic mass of hydrogen. What about the total mass? That is 7 into 12 plus 1 into 16, that is 84 plus 16, that is equal to 100, that is a gram per mole. That is the molecular mass of the heptane. What about the molecular mass of the octane? Molecular mass of the octane, similarly, molecular mass of octane, that is given by C8H, that is 18. Similarly, you can calculate, that is 8 into atomic mass of carbon, 8 into atomic mass of carbon plus 18 into atomic mass of hydrogen, 18 times of atomic mass of hydrogen, 18 times of atomic mass of hydrogen. What is the atomic mass of carbon? That is 12 plus 18 into atomic mass of hydrogen, that is 1, that is 96 plus 18, that is equal to 8 plus 6, 4, 1 carry, 1 plus 1, 2, that is 104, that is a gram per mole. That is the molecular mass of octane. Molecular mass of octane is equal to 104. This is very important. C7H16, that is 100, C8H18, that is 114. This is gram per mole. Now in your problem, they mentioned 26 gram heptane and 35 gram octane. Now we have to calculate the total number of moles. Total number of moles. There is 100 gram of heptane. 100 gram of heptane, that corresponds to 1 mole. According to the definition, this is 100 gram per mole. 100 gram of the heptane, that corresponds to 1 mole. Therefore 26 gram of heptane corresponds to how much mole? How much mole? That is 26 divided by 100. 26 divided by 100. Assume that is x. X into 100, that is equal to 1 into 26. Have to calculate the value of the x. That is 1 into 26 divided by 100. What is its value? It is equal to 26 by 100, that is 0.26 mole. 0.26 mole. 0.26 mole. Similarly, I have to calculate 35 gram of the octane. Similarly, I have to calculate 35 gram of the octane. 35 gram of octane is equal to how much mole? Is equal to how much mole? You know that 114 gram of octane corresponds to 1 mole. Therefore 35 gram of octane corresponds to how much? 35 gram of octane corresponds to how much? Assume it is the x. Therefore x into 114, that is equal to 1 into 35. 1 into 35. What about the value of the x? That is 1 into 35 divided by 114. That after simplification, it seems to be 0.31. 0.31 mole. Now the final conclusion is C7H16 heptane, that is equal to 100 gram, that is equal to 0.26 mole. Similarly, octane C8H18, that is equal to 114 gram, that is equal to 0.31 mole. 0.31 mole. Now we can calculate the mole fraction of the heptane separately and mole fraction of the octane separately. Now how to calculate the mole fraction of the heptane? Mole fraction of heptane. Mole fraction of heptane. That can be calculated by number of moles of heptane divided by number of moles of octane plus number of moles of heptane. Number of moles of heptane. You have the formula Na is equal to, that is XA is equal to Na divided by Na plus Nb. Na plus Nb. Now what about the mole fraction, number of moles of heptane? That is 0.26 divided by 0.26 plus 0.31. That is 0.26 divided by 0.57. 0.57. What is this value? 0.456. 0.456. I think 0.456. 0.456. Number of moles of octane. Therefore, number of moles of octane, that can be calculated very simple by using 1 minus XA, that is equal to 1 minus 0.456, that is equal to, that is 0.544. 0.544. This is about the mole fraction of the heptane. This is the mole fraction of the octane. Therefore, mole fraction of heptane is equal to mole fraction of heptane is equal to 0.456. Mole fraction of the octane is equal to 0.544. 0.54. Now you know about the mole fraction of the heptane and octane, and also you know about the pressure exerted by these two pure components, and hence you can calculate the vapor pressure. Therefore, vapor pressure is equal to what? Mole fraction into total pressure. Mole fraction into total pressure. Therefore, vapor pressure is equal to pressure. Vapor pressure of heptane, that is given by means of P1 or the PU heptane. P heptane is equal to, P heptane is given by P naught heptane into mole fraction of heptane. Mole fraction of heptane. What about the P naught heptane? P naught heptane is given here. Heptane 105.2. 105.2 kilopascal into mole fraction of the heptane, that is 0.456. 0.456. After multiplying these two components, we have 47.97. 47.97, that is in terms of kilopascal. In terms of kilopascal. Similarly, the partial pressure of the octane is given by, means of, that is a P naught of the octane, into mole fraction of octane. What about the P naught of octane? P naught of octane is equal to 46.8. 46.8 into mole fraction of the octane 0.544. Multiplying these two, we have partial pressure 25.46. 25.46 kilopascal. 25.46 kilopascal. This is the partial pressure of the octane. This is partial pressure of the heptane. Therefore, total pressure is given by partial pressure of the heptane plus partial pressure of the octane, that is equal to 47.97 plus 25.46. The total value would be 73.43. 73.43, that is a kilopascal. That is a total pressure of heptane and octane when both are mixed. This is the total pressure. These are the numericals. Okay. Thank you. Then we will continue the colligative properties of the solutions in next period.